Hello, my name is Adam Berkovic, and this summer I have been working on a project through the Nuclear Engineering and Radiological Sciences Department at the University of Michigan, under the mentorship of Professor Alec Thomas. The project I have been working on is to measure atmospheric neutrons by way of attaching a neutron detector to a weather balloon and sending it into the atmosphere. So, why do we care about atmospheric neutrons? Well, neutrons play an intrinsic role in the creation of carbon-14. When neutrons come into the atmosphere from reactions in space, they come into contact with nitrogen-14, resulting in a nuclear reaction where carbon-14 and a proton are the products. Other reactions are a possibility, but this is by far the most common fate of atmospheric neutrons. So, why do we care about carbon-14? Carbon-14 is a radioactive element with a half-life of 5,715 years. Carbon-14 is a fraction of atmospheric carbon, being created and decaying at a constant rate. Carbon-14 is not a fraction of fossil fuel carbon that is put into the atmosphere. Because of the increased amount of carbon-14 free carbon being released into the atmosphere, the fraction of carbon-14 is decreasing. By studying the amount of carbon-14 in the atmosphere, we can study how we are increasing the amount of carbon in the atmosphere, and it all starts with neutrons. Another reason to study atmospheric neutrons is because of how they affect airplane instrumentation. Sometimes a high-energy neutron will hit a semiconductor and affect and change the atoms that make that semiconductor. This can cause a memory error, or sometimes even cause a hardware error. What's more, an error can go unnoticed for long periods of time, creating unreliable data. This can be dangerous, so airplane manufacturers have to take neutron flux into account when building their planes. Neutrons can be difficult to detect because they have no charge. Usually, some kind of reaction is needed to detect the presence of neutrons. Though there are many different reactions that can be used, I'm going to focus on the helium-3 reaction, the one we are using in our detection. Helium-3 has a very high cross-section for thermal neutrons. It is the best neutron detector available. When a neutron comes into contact with helium-3, it splits into a proton and a triton, with 765 kiloelectron volts of kinetic energy in the proton and triton. The detector's shell is made of metal, in our case aluminum. When the detector has a high voltage going through it, the energy produced by the reaction can be recorded. A challenge we first had was finding a helium-3 detector. Helium-3 is a very rare element. It is only 0.000134% of the helium on Earth. It is needed for neutron detection, creation of tritium, which is vital for fusion and fusion research, and in medical imaging. Because of how rare it is and how sought after it is, it can be very expensive to get your hands on a helium-3 detector. We were lucky that Professor Mike Hartman of the Nuclear Engineering Department let us borrow a detector. Our second major challenge was the electronics for the detector. Neutron detectors need high voltages to run through them, so the ions created in the detection reaction can be recorded. Furthermore, a preamplifier is needed to amplify the signal so that the energy is substantial enough to be recorded. This equipment is readily available. The problem is that a weather balloon only has a lift capacity of 4 pounds, and this equipment usually doesn't have a need to be lightweight. It took a bit of time, but we tracked down a product called the PMI-30 pulse detector and high voltage supply. Another challenge is the way we are going to collect the data. We need some memory storage device that can operate well at high altitude and in varying temperatures. We decided the Arduino microcontroller was a good fit for our application. This device can effectively make sure that we record the number of neutrons per second as a function of altitude, and can keep all the instruments calibrated correctly. This project is still a work in progress, as some of our equipment took some time to track down and still has not yet arrived. Updates will be coming about our results and what they mean.